Hey everybody, welcome to Dakari's 32nd virtual fire investigative training session. Today we have Cameron Novak, a senior electrical engineer and fire protection engineer with ATF's Fire Research Laboratory. ATF has recently put out a safety bulletin, a technical bulletin, and the technical bulletin is on the safe handling, transportation, and disposal of lithium ion batteries after they've been exposed to fires and explosions. And Cam's going to take about an hour and tell us about that. So, Cam, go ahead and take it away.
Thanks, Bill. Thanks for having me, everybody. Hopefully nobody's getting sick of me quite yet, but Bill and I had talked about maybe putting something out there to just cover the tech bulletin in a little more detail. We'll do a slight review after Mike Abraham's prior lithium ion battery lecture that he had done for Dakari. We'll just do a very brief overview, and then we'll kind of get into looking at what evidence is left and how to handle that, and briefly talk about just the failure analysis type of stuff. So, just to kind of a quick recap, there's two different types of lithium cells out there. So, primary cells are the single use only, those are lithium metal. And then secondary cells are the ones that we're typically more exposed to or deal with, in that they can be recharged and reused. So those are the lithium ion cells and batteries. And obviously, we tend to hear more about the lithium ion stuff because that seems to be what is failing due to various forms of abuse from the end user. Again, just a quick recap on the components. So you're going to have a positive electrode, and some sort of material is going to be coated or deposited on an aluminum current collector. And then you'll have a negative electrode where you've got graphite or carbon coated on the copper current collectors. So the lithium salts that are actually used to make the battery are coated onto that positive electrode. And then we use the carbon on the copper or the negative electrode. We have a separator, which, just as its name implies, acts as an insulator between the positive and negative electrodes. And that prevents current from flowing within the cell or the battery, but it allows ions to flow between the positive and negative electrodes. And if I have ions flowing inside the cell, I can and then have electrons flowing outside the cell in the circuit. And that's how we're actually able to get some useful information or use out of that battery. And then we have the electrolyte, and that's actually what facilitates the lithium ions to move between the electrodes. So those are the four main components that actually allow a cell to work. And that's what we're going to kind of focus on here. The types of cells that we deal with, I think everybody's most familiar with the cylindrical cells. Those, as you see here, we've got three different sizes. The numbers denote the diameter and the length of the cells. So the 1865, or what we commonly refer to as an 18650, that's 18 millimeters in diameter, and it's 65 millimeters in length. The way the International Electrical Standard goes or is used to denote the sizes is it's 18 millimeters in diameter and 65 or 650 tenths of a millimeter in length. So hence the extra zero at the end. We have prismatic cells, and then we also have pouch cells. And then last but not least, we're going to have lithium metal coin or button cells. So cylindrical cells, prismatic, and pouch cells, those are typically lithium ion. Secondary cells, they can be recharged and reused. The coin or the button cells, those are typically lithium metal, one-time use, and then they have to be disposed of. So one thing that's worth noting, and this kind of plays into the failure analysis and the failures and the handling of them later on, is knowing what the voltages are of a cell and what the state of charge is of a cell. So the nominal voltage of a Lithium cell is around 3.6 volts. That's the top end voltage. But when they're fully charged, they actually can have a voltage up to 4.2 volts. So that's your voltage characteristics. And then on the low end, when you're essentially fully discharged, you're actually not at 0 volts. You're at around 2.5, 2.6, somewhere in there, and that's all manufacturer specific. Capacity of a cell is going to be measured in amp hours or milliamp hours. And in order to increase capacity or increase voltage of a battery pack, we connect battery cells in series. And then I connect them in parallel to increase capacity. So in the middle here, you see I've got 3.6 volt cells. If I connect those in series, I get a 7.2 volt battery pack rated at 1 amp hour. Compare that to on the bottom here, I will have a 3.6 volt battery pack rated at 2 amp hours. Why that's important is that will come into play. From a voltage standpoint, we need to know what the state of charge is, or in an ideal world, we would know what the state of charge is, but we need to know what the state of charge actually means. So 100% state of charge, as you can see on the graph here, is around that 4.2 volts. And as I said before, 0% state of charge is not 0 volts. It's somewhere around 2.5, give or take, depending on what the manufacturer designs their batteries or their cells to be at. This is important because you can actually over discharge a cell or a battery, and that can lead to an internal failure. You can over discharge them and you actually end up with a negative state of charge. That leads to damage internally to the battery and makes it more susceptible to failure later on. So again, 100% state of charge around 4.2 volts, 0% state of charge somewhere around 2 to 3 volts. So this is just, again, kind of reiterating some more and expounding on that previous slide. If I take 4 cells and I connect 2 of them in series, and then I take that series connected circuit and I connect those 2 in parallel, now I have a 7.2 volt battery at 2 amp hours. So all we're doing is adding to this and creating different series connected and parallel configurations to get the battery packs that we need for our desired product. Why that matters is when I go to a fire scene and I start encountering cells all over the place, and 18650 cells are very common in power tool batteries. I need to know how many cells should I have, and if I have accounted for all of them or have some flown off and started spot fires or been kicked or whatever the case may be. So I need to know how many cells should I be looking for. So typically it's pretty easy to know what voltage a battery pack or device needs. Most people know, I'm a Milwaukee, I've got an 18 volt kit, or I've got a 12 volt kit. So that's pretty easy in that sense, because you know that all you have to do is divide that voltage by the nominal voltage of your cells. So as you can see here, with an 18 volt Milwaukee pack, 18 divided by 3.6, I end up with 5 cells. This gets a little screwy here. DeWalt's 20 volts. If I divide 20 by 3.6, I get 5.5. I can't have 5.5 cells. But what's kind of funny is that DeWalt uses that very top end voltage, 4.2 volts, to do their math. So if I divide 20 by 4.2, I get 5 cells. If you were to take a brand new fully charged Milwaukee battery and a fully charged DeWalt battery, the Milwaukee being 18, the DeWalt being 20, and I put a multimeter on them, they're both going to read approximately 20 volts. So in essence, Milwaukee kind of undersells their product, and DeWalt gives you, here's what we can do. Not a marketing ploy for either one. It's just That's what's kind of screwy with their labeling. So you can see here, both of these have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5 series connected cells to get the rated voltage. You can see here, this Milwaukee pack just has a higher ampacity or capacity in that I have 2 series connected strings of cells compared to this DeWalt with a single series connected string. So that just essentially doubles the capacity of this battery pack compared to the 20-volt DeWalt. So again, we know that for an 18 volt or a 20 volt pack, I need to have 5 cells in series. So now I need to know how many series connected strings should I have. In this case, this is a 5 amp hour or 5,000 milliamp hour pack. It's tougher to tell how many you need or how many strings we would need, because individual cells can have different amp hour ratings. So I might have a 1000 milliamp hour cell, or I could have a 2500 milliamp hour cell. In this case, I know this because I disassembled one of my own battery packs that finally bit the dust. So I know that that cell had a 2500 milliamp hour rating. So I know then that I need 2 strings to get my 5000 milliamp hour rating. So that's where it gets a little bit trickier. It's a little bit easier to know, hey, it's a standard, uh, you know, power drill or sawzall or something like that. Those are typically going to be either 1 string or 2 strings, and then they can change the capacity by getting larger or larger cells with more capacity. Like I said, maybe a 1000 amp hour milliamp hour cell versus a 2500 milliamp hour cell. When we get into the bigger packs, like the 40 volt packs or something like that, again, we're increasing the series connected string, but maybe now we have 3 or 4 parallel connected strings together here to get that larger capacity for that pack. So failure wise, what we're worried about, or what can cause a lithium ion failure, is electrical abuse, mechanical abuse, and thermal abuse. And there's different um, levels of each, or different ways to approach those. So this is kind of a nice diagram in that mechanical abuse is going to be covered by crushing, penetrations, dropping it, something that causes damage, which can lead to deformation and separator tearing, or maybe you're just punching through the separator. Electrical abuse can be an internal short circuit. So I have some sort of metal burr that maybe during the manufacturing process, a metal burr got inside the cell, and that eventually works its way through the separator and shorts the 2 electrodes. We can also overcharge a cell. We can over discharge a cell. And then thermal abuse is going to be some sort of environmental heating, whether that's overheating just due to the environment, or maybe I'm trapping the heat that's made during the normal charging or discharge process, and the battery is not able to dissipate that heat, and then that leads to separator breakdown. And those can all lead to thermal runaway. And that's where we get most concerned. If a battery fails and it stops working and it doesn't do anything, shoot, I'm out of a battery pack. But if thermal runaway occurs, and thermal runaway is essentially the uncontrolled generation of heat, that we're not able to dissipate that in a manner that is safe, and now we're just essentially, this thing's going like gangbusters. So what this, obviously it's a concern with a single cell, but when we have a battery pack, I can now have cascading failures of adjacent cells, because thermal runaway in one cell preheats the next cell, which causes that one to go into thermal runaway, which then causes the next one. And so we can have this cascading failure that goes on and on and on until all the energy is used up in that battery pack. What research has shown is that the higher the state of charge of a battery or a cell, the more energetic the thermal runaway is going to be, the greater propensity for ignition of available combustibles nearby, the more mass you're going to lose in a cell or that uh, fails, and you can actually get thermal runaway to start at a lower temperature. So maybe I get at 100% state of charge, I might be able to kickstart thermal runaway at say 140 degrees Fahrenheit, but at 30% state of charge, it might take 170, 180, 190, something like that. So the higher the state of charge, essentially, the more susceptible that cell or battery is to failure. So just wanted to kind of show some examples of what these hazards might be. This is a body worn camera footage where there is a electric vehicle in this garage, and you'll see it's off gassing. It's generating heat. It's generating the gases produced by the cells as they overheat. And you'll see what happens if you get too many of these gases in a confined space. So you see there that firefighter was extremely lucky. Essentially, this electric vehicle here in this garage, again, it's producing these combustible and flammable gases. And if they get to a right concentration, they can lead to an explosion. And something ignited those, whether it was venting, the explosive venting of another cell served to ignite the gases. And that blew the door off. And luckily, he was facing the other direction. Um, so as I said previously, lithium products have a design window that they need to keep their voltages in. So again, I'm just using an example of maybe these cells have a 2.5 volt voltage at 0% state of charge. When you build a battery pack, you want to get cells that have similar voltages and have similar internal impedances. And the reason is I want them to be matched as best as possible, because if I have one cell that maybe doesn't hold its charge as well as the rest of the pack, that cell can get discharged faster than the others. And now I have the potential to over discharge or overcharge the associated cells or that particular cell. This is where it's very important. We had a lot of problems with this when the e-cigarettes first came out, because a lot of them shipped with USB cords but no charger. And if these are rated for 4.2 volts and you just plug it in your computer, a typical USB port puts out 5 volts. So we could potentially be overcharging these devices, or maybe it puts out too much current. And this is just kind of a pet peeve of mine these days. I received a product for my birthday this year, and it said in the manual, must match with a charger that produces 5 volts at 0.5 amps, so half an amp. But it didn't, all it came with was a USB cord. It didn't come with a charger. I'm like, if you're going to be that specific, give us the charger. Because it's hard. Most cell phone chargers these days are putting out anywhere from 1 to 2 amps. So it's really hard to find stuff that'll work safely with these products. So this is an example of an over discharged cell phone. This was an iPhone 4, I believe. And when I play the video, you'll see essentially this video is only a year or two old. So here we are, 2023, 2024. An iPhone 4 is probably at least 10 years old, if not more at this point. So if this phone has been sitting in a drawer for, let's say, 5-10 years, because I believe it's even older than that. So let's say they keep getting the new phones as they come out, but they hold on to this one. If I let this thing sit in a drawer, it will slowly over time self-discharge. And so the battery can actually get to a negative state of charge, which can lead to internal damage. And when I go and charge it, I can now get a failure. Fortunately, this looks like it's on the counter. Probably isn't going to go anywhere beyond what it just did, but it gives you an example of what we're concerned about. Mechanical abuse, penetrations, crushing, drops, everything like that. Fido, getting a hold of your battery or your e-cigarette or something else can lead to a bad day. And I hate to say it, but there are numerous videos like this where a dog is chewing on a lithium battery device that leads to a failure. In this case, this is kind of lucky in the sense that had this dog been on the couch, that room would probably flash over, those dogs would die, and the everything would be a total loss. Given that they're on the carpet, carpet has to go through some flammability testing and meet flammability standards. That carpet's probably not going to do anything, so they'll have some minor smoke damage within that home, but that'll be about it. Okay, so thermal abuse. Again, just like the voltage, there's temperature limits to these devices. So we can generate excessive heat from either use or overcharging or just charging during a normal charging process or limiting the cooling during the charging process. So that you can see in red here, this is actually a headline that just within the last year and a half or so, where, and the problem is typically, particularly with this first thing, charging a phone while it's under a pillow, it's our kids, our teenagers who can't put their phone down until they fall asleep and then they shove it under their pillow. Well, that phone is generating heat as it charges, or the battery generates heat while it charges. And that if it's not able to dissipate that, it can overheat, cause a failure of the separator, and lead to a short circuit. Similar with laptops. They have vents in the bottom to keep cooling the components inside in the battery. And if you limit that by putting it on a carpeted floor and now all those vents are blocked, the computer is no longer able to dissipate heat. Or charging a phone in a hot vehicle. So all those things can lead to failures that we're going to be concerned about. So here's an example. You leave your phone on your dash on a hot day, and this isn't charging, but you can see.
First, here are some examples of devices.
Oops. I'm fortunate to say my phone never caught fire on my dash, but I know that if I put it on my dash in the middle of the summer, it gets quite hot. And sometimes my phone is even shut down and said, hey, I'm too hot. I'm going to shut down until I cool off to a certain temperature. So they do have safety devices built in, but sometimes those aren't even enough. Hobby batteries. So most of those failures are typically seen during or immediately after charging. Hobby shops sell these fire bags, and frankly, they're no longer limited to hobbyist batteries. You can get them for anything. For our on the national response team, we have a couple of UAVs that our NRT members, actually the batteries stay in a little, essentially a fire bag, but a little Kevlar or Nomex bag to help contain any sort of failure. And even on airliners, airplanes now, commercial airplanes, they've got these in case somebody's phone starts cooking off while you're up in the air. So, the guidance that they have on a lot of hobbyist websites, don't leave your batteries charging unattended. Put them, I've heard of recommendations that put them in a cinder block, a hollow cinder block with a piece of wood on top. So at least All right, so we got cut off there. Just to reiterate, I was saying, our national response team has UAVs. We've got fire, essentially a fire bag or a bag to contain our batteries. They have those on commercial airplanes now. So if something happens to catch on fire or fail on a flight, they can try and contain that to a certain degree. There's guidance out there that you shouldn't leave your batteries unattended, even going so far as to place your batteries inside a hollow concrete block with a piece of wood on top. So if it happens to burst into flames, it's contained outside. I've got a friend over in the UK who I've seen him, he's posted pictures where he'll charge his batteries on his gas grill with the lid closed. Obviously, the grill is off, but at least if something were to fail, it's contained within that enclosure. And with hobbyist batteries, you can actually buy special chargers that charge or look at the individual cells within a pack and make sure everything's at the same voltage so that we don't get overcharged or over discharged. All right, so preventing lithium failures or preventing failures of lithium ion products. The big thing here is that batteries, you should never charge a cold battery. And it should always be warmed up to room temperature for a few hours, because if you charge a cold battery, you can actually get plating of the lithium, which can form dendrites or little icicles essentially that can over time, if you keep doing that, those dendrites can get bigger and bigger and actually puncture the separator. Or those dendrites, if you happen to drop that pack later on, that pack is more susceptible to failing because of those dendrites. And it's something that can't be reversed. So it's definitely something to be aware of. On the opposite end of the spectrum, if I'm keeping or storing my stuff or even charging my products in a hot vehicle in the summer, I could potentially get them to go into thermal runaway in that direction. So batteries like to have this nice little window of temperatures that they operate in. Okay, so another thing is if I fully discharge a battery, say I'm running a saw or something like that, and that battery gets warm, which is a normal part of discharging it, I should let it cool off before I recharge it. Again, I don't want to turn around and take a hot battery, put it on a charger, because that could cause it to overheat. And again, most of these batteries have battery management systems that monitor the temperatures. But let's say I decide to buy a knockoff Milwaukee battery or knockoff power tool battery off of Amazon or somewhere off the internet, that might not have the same protection features that a original equipment battery would have. But if I fully discharge a battery and I'm letting it cool off and then I forget about it and I come back a month or two later, that battery, when I left it, was at 0% state of charge, but it can continue to self-drain over time, becoming over discharged. So that also can lead to dendrite formation and plating of metal, which could lead to damage. So overcharging and over discharging, or hot and cold charging, all of these things could be problematic for us. So we have to be really mindful of that. Suppression wise, thus far, it seems like water is the best solution thus far. The issue with pretty much anything like electric vehicles or electric bikes and scooters is you have to get water to the cells to cool the cells that aren't in thermal runaway. So the whole point is you're cooling them to prevent them from going into thermal runaway. Removing oxygen with, like, say, with a fire blanket or anything works great, except lithium products bring their own oxygen to the table. They already have everything they need to cause a fire. They've got the heat, they've got the fuel and the oxidizer. So smothering them doesn't really help. The only thing that we can do to stop is cool them. And again, what experience has shown us is that, and Mike mentioned it in his lecture, is you could have, let's say I have an accident with an electric vehicle and I tow it off to the impound lot or wherever. There wasn't a fire maybe right off the bat, but I damaged that battery pack, and then maybe a month later, now the battery pack goes into thermal runaway. So it can happen days or even weeks later after the incident that something happens. So with the continued monitoring, maybe via thermal imager, is important, because we can use that to say, hey, if maybe this has been cool for a while, we can maybe stop the application of water. But if you now haul that electric vehicle someplace, you're probably still going to want to segregate it in the far corner from everything else, just in case it goes in a thermal runaway. All right, so from an investigation standpoint, it's important to gather as much information through interviews as possible. So you're going to want to figure out who made the product, how old was it, when was it last used, how was it used, are they using, I've seen it, and I can say I'm guilty of it myself, but have you ever used your drill and the battery as a hammer? Probably not a good practice. Does the owner or the last user know what the state of charge was at the time that they stopped using it? At the time of the incident, was it charging? How long it had been charging? Or was it on or off a tool? Things like that. What's the environment that it's left in or stored in? That could be important. And then, do they have anything like, hey, I dropped it 3 hours before the fire? Things like that could be important. And then I want to know what happened before, during, and after the incident. So did somebody do anything to the charger or the battery device? Did they remove it or unplug it or anything like that? All that's good interview information to gather as you start your investigation. You're also going to want to, first step is probably to determine how many cells you should have and then locate those cells. You can use x-rays to figure out, am I missing anything? It can also help you to determine how to disassemble a pack or locate, where are the components that I should have, or figuring out where they should be. And we can get exemplar batteries to figure out, as a comparison, to figure out what we should be looking for. From a failure perspective, unfortunately, nobody has come up with the silver bullet of this is what a failed cell looks like that started a fire versus this one is a victim. Unfortunately, all of the damage after the fact looks pretty much the same. So you might have some luck if you disassemble a pack or a cell or you use CT scans. I'll say this, that you should never be disassembling packs or cells on a fire scene unless you've got the training and you've had a lot of experience and you know what you're doing. Most often that should be done with all the interested parties put on notice and present. But really we tend to use a lot of contextual information derived from interviews and visual observations and things like that. If I've got somebody that says I dropped that pack 3 hours or an hour before the fire, something like that, and I maybe have one cell that has physical deformation, if I can show that one cell has it but none of the others do, and I can exclude maybe somebody didn't step on it, that might be an indicator that that cell was maybe the one that kick-started the whole process. As you identify and collect those cells, it's generally probably helpful to somehow label them or identify them so that you can tell them apart in photographs, because frankly, burn stuff in photographs starts to look all alike. So if you can somehow identify them, say with like a paint pen or something like that, that helps to identify them later on. Again, documenting, document. Probably not going to be lucky enough to get serial numbers or lot numbers because most of these have a plastic sleeve on them that's going to be melted off. I don't think anybody's nice enough to stamp anything in the metal these days for us. We're going to want to document the deformation, any holes or shifting of the contents, or if we completely ejected the contents of a cell. And then we're going to want to get dimensions so we can figure out, is this consistent with a lithium cell, or maybe it's an alkaline cell. I would caution you to not use metal calipers because the top and bottom ends of a lithium cell, or any cell for that matter, are the positive and negative electrodes. So if you short those with metal tools, it could be exciting. One thing that I've recently acquired is 3D printed cells, and I got this idea from another fire investigator, where essentially we can 3D print these cells, and now we've got our life size comparison to whatever we're looking at. So now we can, instead of maybe measuring it, we can throw these down in a picture and say, yeah, this is the same size. This would be consistent with this product, or this type of product, I should say. So this is just kind of showing an example. And again, not something that I expect most fire investigators to do on scene, but this is some stuff that can be done in a laboratory, or maybe even seen in a CT scan, where if we disassemble this, you can see here, there's a metal particle that ended up inside the jelly roll inside the cell, and that could eventually lead to a short circuit in the separator, or through the separator. So just something to be aware of. And this came out of this paper here, and this is actually a good paper, just overall discussing the methodology for investigating a fire that is suspected of being caused by a lithium ion battery. So things to consider too. So 18650s, research has shown that they can fly up to 150 feet. This could potentially lead to fires remote from the initial area of origin. So now we might have what looks like multiple non-connected areas of origin because we have cells flying from their original location and now starting spot fires. So we need to locate those. Again, we're probably not going to be able to determine much without doing some sort of CT scan or X-ray and having a lot of contextual information. And there have been investigators out there who have said, if I've got the jelly roll is, the cell puked its guts out and ejected the windings, that means it caused a fire. Or there's a hole melted in the enclosure or torn in the enclosure, that means it caused the fire. And this paper here actually went through and took all of those and said, hey, we set fires in these rooms and exposed lithium cells, 18650 lithium cells to that fire. And every single one of these was a victim cell and had all of these characteristics. So we've shown that this can all be victim, but at the same time, I think all of these can also be causal characteristics, in the sense that they could be seen in a cell that caused a fire. So that's something. The science is kind of still out there. We're still doing a lot of research, and hopefully somebody will come to a conclusion in the near future. Unfortunately, that might be also the time when we switch to a new battery chemistry. So we'll have to see. So here's examples of cells. And typically what we're looking at is, if I've got a cell that looks like this, where it's ruptured, or if it's ejected the contents, we know it failed. We just don't know why. So what we're looking at is the pack as a whole. Mike kind of alluded to this in his lecture. Again, this is just a bit of a review, but we're typically looking at, if I've got, maybe I've got 5 cells where they all look really good, but then there's just one that's maybe a little more whacked than the others, or a lot more whacked, I might be concerned that could be our cell. So that's kind of, we're looking at differential damage within a pack. that could be an indicator of causality, but we have to be sure to look at everything in context. Here's examples of debris from a lithium cell. And after a fire, typically all we have left is, say for a cylindrical cell, we'll have the steel case and then we'll have the copper foil. The carbon sometimes remains on that copper foil, but the only other electrode in there is aluminum, and aluminum is going to melt at a temperature that we see in most compartment fires. So we typically only have one of the electrodes left, if any. And so sometimes you can see, and I was just at a class back in October where we had the foil was actually ejected 10 feet out of the enclosure where we were doing a test burn. So you can have debris flying quite a ways. So here's examples. Here's the end caps and the crimps, and more of the foil. And here's one of the cell enclosures, or the cans, and that just split open quite dramatically, I might, if I say so myself. All right, so again, we're looking at differential damage between cells in a pack. If there's uniform damage, we might be able to say that that's a victim, just because from a fire perspective, a fire is not going to preferentially hit a single cell. It's going to hit the whole pack. Versus if I've got very localized damage in a pack, that area of damage might be consistent with a single cell causing a failure. It is possible. So this is kind of up in the air. I don't know if it's a hard and fast rule. I would say it's not a hard and fast rule, but it's possible that the cell with the least amount of damage could be the one that caused the thermal runaway in the entire incident. Because if I've got an internal fault in a cell, I'm using up the energy within that cell to generate the heat, and that heat can then cause the next cell to start to go into thermal runaway. But because I've used up all the energy in that original cell, it's not going to have any dramatic damage. It's not going to puke its guts out and eject the jelly roll or tear the can or anything like that. But the adjacent cells haven't used up their energy to generate the heat. They're getting the heat from the neighboring cells. So those could have the most damage, even though they were the victims. So it's not a hard and fast rule, but it's something to consider, that when you're doing your analysis, maybe there's one cell that, if they're all significantly damaged, but one maybe isn't, now we can look at, is there the potential of an internal short that led to that heat generation? Again, that's something that needs some more research, but is referenced in that paper here. I thought this was worth kind of going over. Again, Mike kind of mentioned this in his lecture, but these are showing two different test series, where on the left, you've got a series of three images where these packs were impinged by fire. And you can see there's a lot more damage globally to the pack, and the cells actually left, or some of the cells are actually displaced. Versus on the right, you can see there's a lot more localized damage, and these are essentially, one cell was replaced by a cartridge heater to simulate that cell going into thermal runaway and causing adjacent failures of the pack, or adjacent failures in adjacent cells, excuse me. So you can see the localized damage here simulating a failure of a cell versus fire impingement. And one thing we've noticed in several test series is that fire impingement, that tends to soften the plastic housing of the battery, and that can allow cells to displace more readily than if you have an internal failure within a pack, because that heat's coming from the inside and it's localized to one end wherever that cell is failing. So it might mean that if I have fire impinging on a pack, I am more readily able to displace cells, versus if I have a failure within a pack, most of my cells tend to stay in place. And again, these are x-rays showing the same thing. So the same set of battery packs here with an exemplar here, you can see that fire impingement wise, these cells are starting to displace. These have lost or ejected their contents. And then we've got the cartridge heater simulated failures in the lower left, or excuse me, lower right. And those cells are all in place, and maybe just minimal displacement of the cells themselves. And none of them have yet ejected their contents. So some future research, Mike's been working on a lot of this, working with our certified fire investigator candidates. So some stuff that's going on within ATF is looking at various extinguishing agents, gunfire in electric vehicles, and then toxicology in deceased victims. So that's something that's going on. So kind of skipping to some more of the tech bulletin stuff. The big thing here is even post fire, a battery or cell may still contain enough energy to go in a thermal runaway. So you have to handle them very carefully so that you don't intentionally or unintentionally lead to some sort of damage that could lead to a thermal runaway event. Just because they've been damaged by a fire, you can't assume that they are safe. So this headline here, this actually came from about 2 years ago. Fire investigators in Colorado were working a fire. They had a suspected, I believe it was an e-bike or an e-scooter failure, and they were removing the pack from the structure. And right after they had set it down in the snow outside, it blew up in the one investigator's face. Fortunately, he wasn't, too seriously damaged, or excuse me, hurt, I should say, injured. So he was able to walk away from that. But they were doing everything right. They weren't being super careless. They were handling the battery very carefully, and just things finally cooked off. And that's kind of the silly part about this stuff, is you could have the biggest wrecking crew of a suppression team in there beating this stuff up, and you as the investigator could come in and handle this, with kid gloves, and it would cook off on you and blow up. So be very careful with this stuff. From the explosion and the fire hazards, apart from that, we also have a toxic hazard. Excuse me. So we can produce very, very nasty stuff when these batteries cook off. And Mike addressed that in his lecture. So just kind of be aware that we should never handle this stuff with our bare hands. The technical bulletin, we kind of recommend at a minimum some sort of exam glove, whether it's latex or nitrile. And then wearing eye protection, you may have to consider respiratory protection. And then always wear some sort of outer garment. So, a Tyvek suit, a lab coat, something that you can take off and wash, that just is a barrier between you and your skin and whatever is on this stuff. So here's an example. This was actually from the class I taught back in October. And I came in at the tail end of a week-long fire investigation class. And the agency that had done the test burns put a whole mess of lithium ion products and batteries in these cells. And so this is a power tool pack. This has been through a fire, and I showed up the day that I arrived the day they were processing these cells. And when they were done, I said, hey, let's do a little test. We put this pack in a metal garbage can full of water, and we let it sit for 5 days. And even after 5 days of sitting in just plain water, it still had a full charge on it, as you can see here. So, discharging it in just straight tap water probably isn't going to cut it. And it shows that even post-fire and submersion in water, the pack can still retain quite a bit of energy that it presents a hazard. So as far as collecting evidence is concerned, our recommendation kind of follows the U.S. Code of Federal Regulations for transportation and storage. Bag loose cells individually in some sort of plastic bag. Put battery packs, if they're still largely connected, you can put them in an individual bag too. Just make sure that you're not shorting things that could potentially during transport, or packaging them in a way that during transport they could short out and lead to thermal runaway. If you have to ship these items, you have to ship them via ground. You cannot put them on a FedEx plane, because if you send that up into the air and it cooks off at 30,000 feet, there's nothing that crew can do. When as far as storing it in back at your office, facility, headquarters, whatever, at a minimum, somehow segregate anything containing batteries from everything else. So if something does happen to go wrong in storage, you're not taking up, say, your entire evidence vault. They do have commercial products. The FRL has purchased 2 battery cabinets ourselves for storing evidence and stuff related to testing. This is this cell block fire containment systems. This is not an endorsement by ATF. This is just a company that's out there. So that's there are commercial solutions out there that are available for storing and shipping their stuff. So even this cell block also sells kits for shipping battery devices and items. If you're not collecting stuff, it may still be a good idea to find, gather them all up, bag them individually, document and label where they came from so that subsequent investigators know where they ultimately landed. But at least now you've done, say, if you're a public sector investigator and you found all these batteries, you put them in cells, you put them in bags, and this one came from this side of the room, blah, 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 blah. Now the private sector, they have all of them and they know where they came from. But again, the documentation is key there, making sure that everything's labeled and documented. Again, one of the things that Bill had asked me once a year or 2 ago, they were on a scene. They weren't worried so much about collecting these items, but the concern was, what do we do with it? We don't want to leave them and just have them cook off after we leave. So we had discussed it, and the kind of consensus we arrived at was bag them and then put them in the oven. And at least they would be relatively contained within the oven. So thinking about or being inventive with solutions like that, bag them and put them in the oven, put them in the microwave, put them in the bathtub, or put them in a metal can somewhere. The concern is if you put it in, say, a 1 gallon metal evidence can, does that potentially, if it does cook off, have I now created a bomb? Because I've got an enclosed vessel that now could rupture if I overpressurize it from a thermal runaway event inside. So the transportation of items like this falls under 49 CFR 173.185. And so one thing that's important is that the outer package of anything containing a lithium ion or a lithium metal device or battery has to have this UN number, and it has to have this diagram here. So minimum dimensions of 100 millimeters or about 4 inches square. And then where that little asterisk is, that's where you put your UN numbers. And if you don't know, put them all. At least you kind of covered the gamut of what you could have. But we're worried about things that the shipper has to know what they are transporting, so that everything, the outer package has to be labeled appropriately. And anything that comes from a fire or an explosion scene falls under the umbrella of damaged, defective, or recalled batteries. So this is where I kind of tailored my guidance for collecting stuff. Is everything has to be in an individual non-metallic inner package, so plastic bag, something like that, that completely encloses that cell or battery. Then you're putting that, you're surrounding that package with some sort of cushioning material that's non-combustible, non-conductive, and absorbent. So commercial products that are out there specifically for shipping lithium-ion batteries are available. You could use sand, you could use cat litter, you could use vermiculite, as long as it's non-combustible, non-conductive, and absorbent. Those are the criteria. And then all of that has to be in a rigid outer package. Essentially, it's metal, plastic, or wood. You can't use a cardboard box. And then the outer package, on top of having the UN number and this label, has to have damaged, defective lithium-ion battery or lithium metal battery in text that is at least 12 meters tall, so about 1.5 inches. So those are the requirements for packaging and storing or transporting that stuff. And if you're going to ship it, it can only go via highway, rail, or vessel. It cannot go on via air. So that's the biggest thing that I think as an industry we've kind of overlooked is we'll just package this stuff and throw it on a plane, not realizing that it has to be shipped via highway. So one thing that's worth considering is should at least, ask yourself the question, do we need to discharge these cells or batteries either before storage or before disposal? So salt solution is extremely common. The issue with that is it can cause corrosion. And so if we're going to do this before we put something into storage, we're not going to necessarily want to use salt because it's going to destroy whatever evidence we might have left. The research has shown that a solution of baking soda and water tends to cause less corrosion. So that's going to be more helpful for us if we're doing this prior to storage. Another thing that was found to help was ultrasonic agitation. So essentially, that ultrasonic vibrations sped up the discharge process and it reduced corrosion. One way to go about this too is instead of immersing the whole cell or battery, if you can somehow connect leads to the terminals and just put the leads into the solution, now you're not, you're kind of removing the possibility of corrosion to the cell itself. Just have to be careful that you're not causing a short circuit or anything like that. And obviously you have to know where the components and the electrodes are. And it also would minimize contamination of that solution. So that's another factor we have to consider is in my personal experience, when we put that battery pack in the metal garbage can, I had nice, clean, clear water when I started on day one. I think it was a Friday. And when I came back on Wednesday the following week, that water looked like it was full of rust and bubbles and it was kind of nasty. We were going to sample it and test it, and somebody accidentally dumped it. So we were going to see kind of what kind of junk was in there, but didn't get an opportunity to do that. So the guidance for baking soda wise, 78 grams per liter or about 10.4 ounces per gallon. They said going higher doesn't actually get you any faster discharge time or anything like that. But for the standpoint of ease of measuring, you could just say, hey, a 1 pound box of baking soda. I'm not endorsing Arm & Hammer, but a 1 pound box per gallon gets you that solution. There's really no set guidelines on how long to wait. All the testing up to this point has been done on intact cells and batteries, where they're able to measure the state of charge after the fact. We may not be able to do that on a fire damaged battery. So you're going to probably want to wait at least a few days to for that cell to be fully discharged or battery. I know in the paper that references the 78 grams per liter, they said it was 1.1 days to fully discharge a cell. So I think that's your bare minimum. We're probably talking 3, 4, 5 days, something like that. So references, just a lot of stuff that's out there. Most of these you've kind of seen in the presentation already, but I'm happy to take questions. You probably, if you've seen any of these before, you've seen my email. So feel free to reach out if you've got questions, but I think that's pretty well it.
Cameron, killed it, buddy. Really appreciate it. We'll have a test up. Cameron will send me some questions. We'll make this testable training. We really appreciate everybody's support over the past 5 years as we offer up these virtual fire investigative training sessions, and we'll see what the future brings, as long as people like Cam step up and offer their expertise. We'll keep putting these together for you guys. So, hey, thanks a lot, and we'll see you in the next one. Thanks, Cam.
Thank you.